Hello everybody, welcome back. Today we're going to continue our introduction to propulsion, but we're going to develop a definition of thrust, for example, and also some important engine metrics and efficiencies. This will be our last sort of exposition heavy lecture. It'll be a little dry, but then next time we'll be able to really jump into the topic of propulsion and start talking about different engine types and topics like that. But nevertheless, it's important first that we define all of these important figures of merit that you'll be working with and calculating as part of your homework. So let's start by developing a definition of thrust using the Reynolds transport theorem. Develop a definition of thrust using the Reynolds transport theorem, RTT. Okay, so I'm going to draw a nice big diagram here of like a converging diverging nozzle that, let's say, is kind of a abstract representation of an entire propulsion system. Okay, our representations of propulsion systems will get more complex as time goes on, but for now we'll start there. And we're going to draw a big control volume that contains everything except for, say, the physical walls or of the channels of air of the propulsion system. So what I mean by that is that we'll draw a big sort of box control volume. You know, this front surface of the control volume is going to be, you know, relatively far upstream in the free stream. And then what we'll do is we will bring the control volume here, and then it's going to be wetted or along the exterior surface of the propulsion system. And then, like I said, it'll be wetted on the interior surface as well of all of the flow channels within the propulsion system. Okay, and then this surface here is right at the exit, and then the same thing, you know, all around all the propulsion system surfaces. So everything except for the actual mass that makes up the propulsion system is contained in the control volume, or in other words, all the actual flowing air mass. Okay, and so here I'm going to move this over a little bit because I need to label some stuff on the left here. But this area here is going to be denoted AE, or the area of the exit of the propulsion system. And then we will just call this area that's downstream but not out of the exit of the propulsion system, we'll call that A2 over 2 in this case, because we'll have both of these sum up to A2. So A2 over 2. And then this entire area around the front will be equal to A2 plus AE. Okay, so it's just a straight control volume. We will have, here I'm going to actually erase this label here, on the top and bottom by symmetry, we'll have some exiting density out of this area too, an exiting pressure and an exiting velocity. Okay, it may not be uniform necessarily. And then out of the exits, we have the same thing. We have a pressure exiting the system, a velocity exiting the system, you know, a temperature and a density, just an exit state, if you will. Okay. We have entering, of course. We have an entrance state. We'll call it P naught, which this is actually the free stream conditions, not the entrance conditions. Okay, the entrance or inlet will have a different label. But the airflow going into the engine specifically, we're going to call m dot a. So that's very specifically the airflow that goes into the engine, not the airflow that goes around it. And then we also have crossing the control volume boundary inside the propulsion system is a small mass flow rate of fuel and some amount of enthalpy due to, say, combustion in that type of propulsion system. We're going to label this area along the control volume. We'll say that that's A1. And we also have some sort of component of velocity, we'll call it V1y, that is exiting those surfaces of the control volume as well. So we need to keep that in mind. So we have V1y and ρ1 exiting the control volume on that surface. Okay? And then we'll just assume that we're at steady state. Okay? So let's go ahead and like I said, use the Reynolds transport theorem to build up a definition of thrust here. So we just to remind ourselves, the Reynolds transport theorem in general is expressed in the following way, where you have dn dt, where capital N is the property that you're tracking, the extensive property. And then on the right-hand side, you have things in terms of eta. Sorry, I'm just going to move this a little bit. You have things in terms of eta and rho. So you have rho eta dv, okay? The partial derivative with respect to the time of that. And then we also have the transport term, C at the surface integral of rho eta v times, sorry, not rho eta v, just rho eta times this quantity of v dot n hat dA. Okay? So that's the general Reynolds transport theorem. If we apply this to mass, in this case, you have the mass, this integral here, rho v dot n hat dA. This is just the general integral. The time derivative term went away. And then we also have a mass flow rate entering the system. So we subtract that on the left-hand side. And we know that overall that's going to be equal to 0. Okay? So, or in other words, if we summed up all the mass entering and exiting the system, aside from the mass flow rate, you know that you would end up with the only thing that you would be missing is the mass flow rate or of the fuel that's being injected inside the propulsion system. Okay, but in general, mass does not change with time. So the d capital N dt term goes to 0 in the mass case. Okay, and then let's look at momentum. So in momentum, you have the left-hand side of the Reynolds transport theorem, that d capital N dt becomes a sum of forces over the control volume. And so in our case, what you end up with is just the pressure forces, okay? So you have the pressure on the left, which is P naught times A2 plus AE. And then on the right-hand side, you have P2 times A2. So the pressure profile all along area A2 on the right-hand side times A2. And then also the pressure profile or pressure value outside the exit times AE. And then on the right-hand side, and then there's also the friction forces, right? So we can integrate over AW is what I'll say. So what I mean by AW is that's us integrating over the surface, the wetted surface of the propulsion system. And then there you have the stress tensor, the overall stress tensor, which is P, the pressure times the identity minus tau, which is the sort of full stress tensor, dotted with n hat, dA. Okay, so this is this overall term there just calculates all of the forces on this crazy curvy part of the control volume. Okay, so it's everything sort of being abstracted into that one term there. That's what that term is saying. And then on the right hand side, you drop the partial derivative with respect to t term, and then you just have the transport integral term, which is rho v times v dot n hat. Or in other words, eta is just the vector v in this case. Okay, so that's what's happening on the momentum side of, excuse me. And so let's go ahead and peel open these integrals a little bit. So we'll start with the mass. Start with mass. Okay, and then let's talk about what's happening at each of these surfaces. So on the left-hand surface, we're going to assume that we're at sort of a let's say, cruising speed, and that the flow coming in is quasi 1D. So there is no velocity or property profile at the left-hand side of the control volume, the entering flow. So on that side, you're just going to have, for the mass flow rate in, is minus rho naught v, we'll call it vx naught. Okay, so the x component of v naught times a2 plus ae. Okay, so that's your mass flow rate inwards. So in other words, what we're doing right now is we're taking the components of this integral and we're expanding it out. We're actually evaluating the integral. Well, for the A1 surface, the top and bottom surfaces of this control volume, it's a little bit more complicated. So we're going to leave that in integral form for now. That'll be twice the integral over the A1 surface times rho and then Vy1 dA. And the reason we leave it in integral form is because we actually can't make the same sort of assumption here. We don't know what the velocity profile is along that A1 surface. So Vy1 is sort of implicitly dependent on space along that surface. So we'll go ahead and leave that as it is for now. We're also going to apply the 1D assumption to the flow that is exiting the engine specifically. So all of the properties at the exit are uniform over the exit cross section, and so that term just becomes rho e v x e. So the x direction velocity at the exit and area e. Okay. And then again, for the A2 areas, so the areas above and below the exit, we don't know what the velocity profile is going to look like there. So we just integrate that in A2 over, the integral over A2 rather, of rho to V2 dA. And by integrating over A2, I'm integrating over both those A over 2 pieces. Then we'll subtract m dot f, and that thing is equal to 0. Okay, so that's evaluating the chunks of that integral that we know or that we can evaluate. And then we'll also take a look at x momentum. Okay, and evaluate all these terms, especially what's happening here. Okay, and in that case, what you end up with is the following, where you have, and I want to be very clear, this is a negative sign here. It's not on the left-hand side of the mass equation. It's not like a bullet point. Okay, so for x momentum, we end up with P naught times E plus A2. Okay, that was already in the previous equation. The pressure distribution over area 2. So here I actually just wrote it as P2A2, but I actually should have written it this way, where it's the integral over A2 P2 dA, because we don't actually know what the pressure distribution is over that A2 surface. So that was actually a bit of a mistake on my end. This should be the integral over A2 of P dA, P2 dA. Okay. So that's where it's being carried down here. Then of course we're also making that 1D assumption for the exits, which is fine. We also have that really ugly, fancy engine surface stresses term. So we have both the pressures and the shear forces being accounted for here. Dot n hat dA. Okay. And then let's expand what's happening in that integral, like I said. So the first thing is we have the mass flow rate times the velocity entering the entrance. And like I said, the velocity profiles and all of the properties are uniform, or 1D, quasi 1D at that left-hand side of the diagram. So you end up with minus rho naught V naught squared times A2 plus AE on that side, right? So that's just m dot entering times the velocity entering, which is what you tend to get in these integrals when things are 1D. The other 1D term that we have is the exit, so rho E VE times AE, okay? And then we have the right, yeah, sorry, apologies. And then we have those two integral terms that are over the areas that we don't understand. Sorry, I started looking at the wrong spot on my notes there for a second. So we have the integral over A2 of rho 2 V2 squared dA plus twice, or 2 times, the top and bottom integral, which is the integral over A1 of rho 1. And then this is a little tricky here. So we're talking about V2. So this really should be V2x or Vx2, right? So like the V in the x direction. This should be true for all of these, x and x here. This term is actually a little complicated. So the velocity that's carrying it out, that's the velocity that's component that you're pulling out with that v dot n hat part of the integrand. That's Vy1, but we're actually interested in the x velocity that's being carried out. So this term ends up being Vx1 times Vy1, okay, dA. And so the Vx1 is just from this guy here. We're just looking at the x component of this overall term. And then the Vy1 is the fact that we're looking at the top and bottom surfaces. So V dot n hat along that surface is Vy. Okay? So this term here, we actually are going to make an assumption here. So we're going to say that this is approximately equal to 2 times the integral over A1 of rho 1 and then Vx naught, okay, Vy1 dA. And so we're basically assuming that the x component of the free stream is approximately equal to the x component along the surface 1. So basically Vx1 is approximately equal to Vx naught. And that makes sense, right? If this top and bottom A1 surface is far enough away from the propulsion system, you wouldn't expect the x component to be affected much. The air might be pushed out of the way, and you'd get some y component, but the x component is going to be about the same. So that's why we plug in that assumption. Okay. So we're going to use that assumption. Use that assumption, and then we're going to do a couple of steps. The first thing we'll do is we'll multiply the mass equation by Vx naught. So molt mass equation by Vx naught, okay? And then we're going to sub in, for this 2 times the integral over a1 rho 1 Vx naught Vy1, okay? So in other words, we just made this assumption. We're going to solve that entire equation for that term, and then the mass equation, if we multiply that by Vx naught, the a1 integral is going to have the same term in it, and so we can use that to sub in our information from the mass equation and also drop that ugly integral over the a1 surface. It'll get rid of one of those really really unappealing integrals. Okay, so doing these 2 steps, what you end up with is the following, where you have p naught times ae plus a2 minus the integral over a2 p2 dA minus pe ae plus that stress integral pi minus tau dot n hat dA. Okay, and then on the right hand side, we're just continuing to write essentially the same line that we had before. And then we're going to sub in for that last term. So the first 3 terms are the same. We have minus rho naught v naught squared. And I'm going to drop the x subscripts for now. Just know we're still talking about the x direction here. Plus rho e v squared e ae plus that integral over a2 of rho 2 v2 v2 squared dA. Okay, and then this is what the next sort of line that I'm going to do here is coming from the substitution, where we have plus rho naught v naught squared now, a2 plus ae, minus rho e v naught ve ae, minus the integral over a2 of rho 2 v naught v2 dA, plus m dot f vo. Okay, so we see that these terms here are going to cancel, which is nice. These terms on the left, and then we're going to sort of rewrite everything in terms of what's happening here. So that we'll move that over to the left hand side and then express it in terms of everything on the right hand side. So again, what we'll end up with is that integral over a w of pi minus tau dot n hat dA is equal to, and we're going to group some terms here, rho e ve times quantity ve minus vo, or v naught, times ae. That's one term. We're going to have the pe minus p naught times ae term, okay, plus m dot f vo, or v naught, okay, and then one last integral over the a2 surface of rho 2 v2 times the quantity v2 minus v naught, plus p2 minus p naught dA. Okay? Okay, so and then this is where we can kind of, like I said, we've now taken this really ugly integral that we have no idea how to evaluate. And we've even expressed it in terms of things that are way more straightforward. And we're actually going to note something here. So like this thing is literally the pressure and stress acting over the surface of all the engines. So remember, this is pressure and stress acting over entire engine surface. Okay, so it's because it's steady state, this has to be equal to 0, right? So the net forces acting on the engines has to be equal to 0. So since steady state is equal to 0, or else you would have some sort of net acceleration, right? And you can think of it as a balance between thrust and drag. So it is a balance between thrust and drag. Right? So it is equivalent. So we know that this integral, AW, of pi minus tau dot n hat dA, we're going to define these terms, thrust and drag, or T and D, where it's equivalent to T minus D, which is equal to 0. Okay? And then if you look at our expression, we're just going to make some intuitive choices for the thrust component or for the drag component. So intuitive choices for T and D are the following. So looking at this, we have this, we have these, and it's already kind of organized in that way. This stuff here, these three terms, say, are all values that we can obtain by analyzing the engine. Okay? Whereas the flow, the complexity coming from the flow around the engine is all encapsulated in that term. Okay? So that term is going to be the drag, and then the red term is going to be the thrust. So T is equal to rho EVE times this quantity VE minus VO, V naught, times AE plus PE minus P naught AE plus M dot F VO, V naught. Okay, so that's the thrust. And then can get all these values by analyzing engine. And also notice that these are all the areas where we're assuming 1D flow. So everything is uniform and easy to deal with. And then the drag term has all of those non-idealities in it, the non-uniform profiles and whatnot. Whereas just an integral over A2 of rho 2 V2 times V2 minus V naught plus P2 minus P naught, all that whole quantity dA. So all flow around engine complexity lives in that term. Okay. So, in addition, another thing to note, we have from just conservation of mass that the airflow exiting through the exit of the engine, so that's rho EVAE, that's just m dot through the exit, is equal to m dot A plus m dot F. So remember, we defined m dot A as the mass flow rate entering the engine alone, okay? And then m dot F is the fuel injected into the flow. So we can actually rewrite the thrust in the following way, where we have m dot A times VE minus V naught, okay, plus the quantity PE minus P naught, the pressure difference, times AE, okay, plus m dot F times VE, Okay, and you'll see that if you make that substitution into that T expression, you get this. And this is our real equation for thrust that you'll often use, the dimensionalized equation for thrust. Okay, and really, look at this. This right here, you have this term and this term. What are these terms saying here? These are just the momentum change of the air from the entrance to the exit. Okay, so that's what those two terms are essentially telling you. You have the mass, and then also the pressure difference, which is can be a net force on the engine, right? So we almost could have come up with this definition of thrust entirely, completely intuitively, but better to establish it using the Reynolds transport theorem in a rigorous way. Okay, so now if we want to start to develop some measures of efficiency, we need to look at how energy is being transported. So apply the Reynolds transport theorem for energy. So RTT to energy. So this is for efficiency, to develop an expression for efficiency. We're going to neglect the viscous or conduction effects at the control volume boundary. And we'll also assume that the flow does not transfer heat to the engine. Okay, just to make our analysis a little bit cleaner. So if we do that and we sub in our stuff into the Reynolds transport theorem, what we end up with is the following. The dE dt on the left-hand side is just the amount of energy that's being injected into the system by the combustion reaction, which is just m dot f times hf. Okay. hf is a quantity called the fuel enthalpy. Okay. It's defined for for types of material. So like it's the amount of heat released per unit mass, in this case kilogram, of combusted material and sort of tells you what the latent energy content per mass of a certain fuel type is. Some examples, if you look at a very common jet fuel called JP4, this is 4.28 times 10 to the 7th joules per kilogram. Okay. If we just looked at what the fuel enthalpy is of regular old air, okay, which is equal to Cp of air times T at standard temperature and pressure, this thing is equal to 2.896. This is not fuel enthalpy, I should say. This is just the enthalpy of air, period, okay, at standard temperature and pressure. Assuming air is behaving like a perfect gas, this is how much energy content regular air has. And so if you take it the ratio of of JP4's fuel enthalpy to sort of the latent enthalpy in air, it's 148. Right, which basically just tells us that hydrocarbons have a remarkably high energy content. which is like, it's honestly one of the miracles of nature that they have such a high energy content. If, in fact, they have a great energy content, and it's just about high enough so that we can actually leave Earth. If if they had, nature just worked out where they had a little bit less, and the Earth is just as massive and the same size as it is, then we might literally not be able to engineer propulsion systems that we can reach escape velocity with. So it's pretty remarkable. That's a little bit of an aside. I'll continue writing the equation here. So that was the left-hand side of the energy equation, the energy, or the Reynolds transport equation applied to energy, that total derivative part. Then we integrate over the control surface on the other side, where you have rho times the internal energy per mass times v dot n hat dA. And then if we actually calculate this integral, the left-hand side we have the enthalpy of the air entering times the mass flow rate of the air entering. So we have rho naught times ht naught, so the total enthalpy, a stagnation enthalpy entering, v naught times A2 plus AE. Okay, then we have the stagnation enthalpy exiting, the total energy content leaving, rho E HTE, VE AE. Okay, and then again we have those sort of more complex integral terms. The integral over A2, rho 2 HT2, V2 dA, and then the A1 integral as well, 2 times the integral over A1, rho 1 HT1 V1y dA. Okay? So now we're going to make a couple of simplifications. The first thing to do is that we know that the flow, since the flow outside the engine so that meaning the flow that doesn't pass through the center is adiabatic, and that was about that assumption where the engine is not heating up the flow itself. That adiabatic, that means that HT2 is approximately equal to HT naught. Okay. HT2 is approximately equal to HT naught, and because those are equal, essentially all of the components of the enthalpy that's being transported in but not captured by the engine, so therefore the part that's multiplied by A2 in this case, that proportion is going to cancel on the right hand side. So like meaning this part and then these two integrals are essentially going to all cancel out or all fall out. Okay, so like not just HT2 but also HT1 is equal to HT naught. So in the original equation, those go away, and you're left with 0 being equal to rho E HTE, VE AE minus rho naught HT naught V naught times AE minus M dot F HF. And then those two complicated integral terms go away, and you lose the A2 portion of the rho naught term. Okay, so now the next thing we'll do is we'll multiply continuity equation by HT naught. Okay, so this is very similar to what we did before, where we multiplied by that V naught in the x direction. So looking back at the continuity equation here, scrolling up, this is the mass equation that I did here, that I wrote down here. We're going to multiply that whole thing by ht naught. Okay, so it'll end up looking like minus rho naught ht naught v naught times a2 plus ae plus twice integral of a over a1 rho 1 ht naught v1y dA plus rho e ht naught VEAE times plus the integral a2 rho 2 ht naught v2 dA minus m dot f ht naught equals 0. Let me clean that up a little bit. M dot f ht naught equals 0. Okay, and in the exact same thing that I just said before, because of these, the flow outside the engine is adiabatic, the two integral terms go away, and as well as this a2 there. Okay. And then what we're going to do is add, we're going to add this or subtract this from the energy equation. So that's going to make the other term, the rho naught ht naught v naught ae term, get canceled now. Okay. And what will result in is the following. So, and subtract from energy equation. And what you get is the following. 0 equal rho e v e ae times hte minus ht naught plus m dot f times ht naught minus hf. Okay, and then remember that rho e v e ae is equal to m dot a plus m dot f. And we'll make that substitution, and you get the following equation, which is kind of like an energy balance across the engine. M dot A plus M dot F times HTE. Clean this up a little bit. M dot F times HTE is equal to M dot A HT naught plus M dot F HF. Okay, and this is again, this is like an intuitive equation that we almost could have written down to begin with. It's literally just stating that the change in stagnation enthalpy per second of the flow is just equal to the rate of heat injection due to the fuel burn. So, you know, the total energy exiting the flow, that's what's happening on the left, is equal to the energy captured by the engine, the m dot a ht naught, plus the rate of fuel energy injection because of the fuel burning. Okay? So now that we have that energy balance, let's develop some efficiency measures. And this is more of a section in its own right. Okay, so first we'll do is overall efficiency. So the overall engine efficiency is defined as the power delivered to the vehicle divided by the total energy released due to combustion. Specifically, the total energy per second released, or power, total power released via combustion. Sort of a sensible definition, right? And the way you can define that is the thrust times V naught. Okay, so the thrust times your free stream speed, which is like your power delivered to the vehicle, divided by m dot f h f. Okay. So that's a definition of overall efficiency. What about range? Let's talk about range for a second. So let's just, if we make two assumptions, the following assumption. So if we assume that the lift over drag is and the overall efficiency is constant, or both of those are constant. Then the range, which is equal to the integral of the free stream velocity, or the speed of the vehicle, basically, over the flight time, which you can write as the integral of m dot f hf eta overall divided by thrust, okay, using the thrust definition, dt. We can then basically rewrite this, perform the integral, that is, or rewrite this, I should say, because we note that the lift value is equal to the weight, right? And the thrust is equal to the drag. So thrust, which is equal to drag, which is equal to drag divided by lift times the lift, which is equal to the drag divided by the lift times the weight, okay? And also, the time rate of change of the weight is equal to minus m dot g. Okay, so m dot meaning the time rate of change of the aircraft. If we substitute all these things, you end up with the following, where you have minus eta overall times hf over g times the lift over drag ratio times the integral from W initial to W final of dW over W. Okay, that's making this assumption here. Then what you get for the overall range is eta overall times hf over g times L over D times the natural log of W initial over W final. Okay, so this is like this is Charles Breguet's range formula, who actually founded Air France in 1919. So, but that's a range formula due to Breguet. So essentially, as your weight increases, to maintain as your weight decreases, to maintain the constant lift over drag value, your altitude has to increase, accompanied with a corresponding decrease in required thrust. Okay, it's just the dynamics to kind of keep this all the same. Okay, let's define a propulsive efficiency and the thermal efficiency. So we're going to split the overall efficiency into two parts. So into an aerodynamic component and a thermal component. So eta overall is equal to eta propulsive times eta thermal. Okay. The propulsive efficiency is defined as the power delivered to vehicle divided by the jet power. Okay. And what is jet power? Jet power is the change in propulsive fluid kinetic energy. Okay. So again, the numerator is just TV naught, and then this is divided by m dot air times VE squared over 2 minus V naught squared over 2. So the air that passes through the engine, it changes from having initial velocity V naught to VE. So this is the change in kinetic energy of that that component of the propulsive fluid. And then you also have the change in kinetic energy of the fuel, which is injected at, energy 0, say, and then it's accelerated to VE squared over 2. Okay, so that's what the propulsive efficiency is. And then one thing that's interesting about the propulsive efficiency is that if we assume that m dot f is much, much less than m dot a, which is true, of course, in practice, or in most cases, I should say, and that the flow is perfectly expanded. And as we've discussed before, that means that the pressure at the exit is equal to what you actually have at the receiver, which in this case is that same atmospheric pressure that we're going into. So that's PE being equal to P naught. Okay, then the propulsive efficiency equation simplifies a lot. So eta propulsive being equal to m dot a V naught times V E minus V naught. So that's the thrust equation with these assumptions put in, okay, times V naught. And then the bottom equation, m dot a over 2 times VE plus V naught times VE minus V naught. So that's expanding the difference of squares there. The m dot f term on the denominator went away because we assumed that m dot a was much, much larger than m dot f. And so these two things cancel, and then as well as the m dot a's, and the propulsive efficiency just becomes this ratio 2 V naught over V naught plus VE. Okay, and then as VE approaches V naught, your propulsive efficiency goes to 1. Okay? In this case. And then, excuse me, for the thermal efficiency, we have jet power on the top now, divided by heat added via combustion. Heat transfer due to combustion, which is this, it's the same denominator as before. You can kind of see how these cancel to form the overall efficiency now. So the numerator is m dot a times VE over 2 squared minus V naught over 2 squared, or V naught squared over 2, plus m dot f VE squared over 2 divided by m dot f HF. Okay, so that's how we define thermal efficiency. Now remember, recall that the expression for the eta thermal of a general thermodynamic cycle is the following. So recall that general eta thermodynamic, let's say, is equal to the amount of work you get out divided by the amount of heat you put in, which is just Q in minus Q rejected over Q in, which results in 1 minus Q rejected divided by Q in. Okay, it's like a generic definition. And what we can do is we can rearrange our thermal efficiency to look like this. Rearrange, we'll call this, let's call this star, just so we can, so we rearrange star, we get eta thermal is equal to 1 minus m dot f HF plus m dot a V naught squared over 2 minus the quantity m dot a plus m dot f VE squared over 2 all divided by m dot f HF. Okay, so remember that our total enthalpy is written as H naught plus V naught squared, right? So recall ht naught is equal to h naught plus v naught squared over 2. So we can actually sub in for the v naught squares, bring in the actual total enthalpy. So then that means that this is also equal to 1 minus m dot f hf. That's hard to read, sorry. M dot f hf plus m dot a times the quantity ht naught minus h naught plus the quantity m dot a plus m dot f times hte minus he, all divided by m dot f hf. Okay, we're getting there. Then we use that energy balance that we evaluated. I said we needed this to develop an efficiency metric, right? So if we use that energy balance, we can use energy balance. And if we do that, we end up with the following eta th, which is 1 minus m dot a plus m dot f times he minus h naught plus m dot f h naught divided by m dot f hf. Okay, so looking at this, we can see that Q rejected in this case is the same as m dot a plus m dot f times he minus h naught plus m dot f h naught. So our rejected heat consists of mass carrying excess energy into the exhaust. And then this is the fuel mass carrying out excess enthalpy. Okay. And then the second term is basically resolving the paradox of this not, truly being a closed system. So the fuel mass is carrying out some of that excess enthalpy. All right, so a few different ways that you can use to express the thermal efficiency here, but mainly we just wanted to make sure it kind of helps us have an idea or a better understanding of where the energy is flowing in the system. As the last thing that we'll talk about before we're done here is do some non-dimensionalization. Non-dimensionalization is often nice, especially in this field where there can be all sorts of different unit systems. So we can not have to deal with the unit problems. So for thrust, recall that we had T is equal to m dot A times VE over V naught plus PE minus P naught AE plus m dot F VE. Okay, what we're going to do is we will normalize this by P naught A naught. Okay, so A naught is the capture area. It's not the area of the inlet of the engine. This is 1 over P naught A naught times this, and let's sort of expand our definitions here. We'll have rho naught A naught V naught squared times VE over V naught minus 1. Okay, trying to make everything non-dimensional here. AE over P, or AE times P naught divided by PE over P naught minus 1. Okay, we're pulling out those things. Then we'll have this factor F, which I'll define in just a second. Rho naught A naught V naught squared times VE over V naught. Now, F is what we're going to call the fuel ratio, and it's just equal to m dot F over m dot A. Okay. Often we'll be assuming that F is very small. Okay, then we'll bring in the ideal gas law equation of state, believe it or not, to deal with the density. So we'll have gamma P naught A naught V naught squared over gamma RT times this quantity 1 plus F VE over V naught minus 1 plus AE P naught times PE over P naught minus 1. Okay, then we're going to have this guy cancel with this. And our final non-dimensionalized thrust equation is that you'll be calculating over and over again is T over P naught A naught times gamma M naught squared. Okay, remember that gamma RT is just A squared here. So that's where the M naught squared is coming from, times the quantity 1 plus F times VE over V naught minus 1 plus AE over A naught times the quantity PE over P naught minus 1. Okay, so you'll use that equation quite often. And again, this A naught is a capture area. And we'll talk about that later. ISP, or specific impulse. This is usually expressed as is non-dimensionalized in the following way, where you have ISP G over A naught being the speed of sound. We can rewrite this as 1 over F T divided by m dot A naught. Okay. Because remember that ISP itself is m dot thrust divided by m dot fuel, and so F times m dot A is m dot fuel. Okay. And then the G gets rid of the m dot fuel times G. So ISP is normally defined as thrust divided by m dot F times G, right? So that's how you end up with this thing. And then this this becomes 1 over gamma m naught T over P naught A naught. Okay, so you can write, this is how you can write or translate between the non-dimensionalized thrust and the ISP in a non-dimensionalized way. Okay. Yeah, that makes sense. I was just making sure the units worked out between G and A there. Okay, so that's one thing. I think, yeah. And then there is, of course, the overall efficiency. One thing that actually I'll leave that to you guys. You guys can think about that one. I think it'll be relevant for homework later. This relationship between m dot a naught, and p naught a naught times gamma m naught. Like seeing that relationship can. I think I can't remember, but I think it was nice for one of the homework problems. So okay, so writing out the general definition for the overall efficiency. Let's sort of try to write this in terms of our non-dimensionalized versions. So you have T divided by F times m dot A. Okay, and then on the numerator we can have V, and then we're going to multiply by 1. We'll have Cp T naught, so T of the free stream, times Cp T naught HF on the bottom. Okay, continuing to rewrite this, you have T over F times m dot A times gamma minus 1 V naught over A naught squared. Okay, times Cp T naught over HF. Okay, this thing is also an important sort of metric that you'll see over and over again. This is defined as, it's called tau fuel, but in this case it's actually inverted. But you'll see tau fuel is an important, or tau F, it's an important metric for engines. So you have 1 over F T divided by m dot A naught times gamma minus 1 times m naught over tau F, or tau fuel. And finally, for eta overall, you can write this as gamma minus 1 over gamma 1 over F 1 over tau fuel times T over P naught A naught. Okay? So writing the overall efficiency in terms of the non-dimensionalized thrust. Okay, I'm sorry. I know that lecture is super dry, but we're done. And it just has, we needed to get to these formulas so that you can do your homework really and start to analyze these propulsion systems. So my apologies if it was a little dry. There's like one diagram at the beginning and then it's just math. And I know that's not the best when it comes to lecturing, but unfortunately, a lot of these formulas are important, and it's also important that you understand where they're coming from. It'll hopefully make things a little bit more intuitive when you're calculating these figures. Okay, so next time we're really going to jump in and actually start develop some propulsion concepts. So hopefully that'll be interesting. Maybe show some videos, and yeah. So, but we've eaten our vegetables now, and now we can go on and get to the exciting stuff. So, look forward to seeing you there, and thanks for listening, getting through this tough dry lecture, and I'll see you next time.